1.4 billion kilometers from Earth, orbiting Saturn, there's a moon that breaks every rule we thought we understood about dead worlds. Titan has a thick atmosphere, denser than the one you're breathing right now. It has lakes and rivers carved into its surface, weather systems that move across continents, clouds that rain liquid methane at minus 290 degrees Fahrenheit. It's the only place in the solar system besides Earth where liquids pool on the surface. The only moon wrapped in nitrogen haze. The only world beyond our own where organic chemistry happens in the open, building molecules that on Earth became the foundation of life. And then, in 2006, Cassini's radar pierced through that orange fog and found something no model predicted. A landform that violates the physics of a world that cold, that distant, that supposedly inert. To understand what Cassini saw, we need to start with why Titan was impossible in the first place. The impossible moon. Most moons are airless rocks, ice balls held together by their own feeble gravity. But Titan's atmosphere presses down at 1.5 bar, 50% thicker than Earth's at sea level. It's 95% nitrogen, the same gas that makes up most of our air, laced with methane and complex hydrocarbons that form a perpetual smog. This shouldn't exist. Titan's surface temperature sits at minus 179 degrees Celsius. At that temperature, chemical reactions crawl to a near halt. Methane should freeze solid. And Titan's gravity is just 14% of Earth's, far too weak to hold onto an atmosphere over billions of years. Solar wind should have stripped it away eons ago, the way it did to Mars. Yet there it is, a haze so thick that for decades we couldn't see the surface at all. Something keeps pumping methane into that atmosphere, replacing what ultraviolet light breaks apart. Something replenishes what should have vanished into space 4 billion years ago. That atmosphere hides something even stranger beneath it. Voyager's glimpse, November 12, 1980. Voyager 1 screamed past Saturn at 64,000 kilometers per hour. Its cameras trained on the solar system's second-largest moon. Mission controllers had routed the probe specifically for a Titan flyby, sacrificing a trajectory toward Uranus and Neptune for one close look at this enigma. The images came back featureless, solid orange, edge to edge, no craters, no mountains, no variation in brightness, nothing but a uniform photochemical murk 200 kilometers thick. Scientists had spent years preparing instruments, mapping flybys, arguing over what they'd find. They got a blank wall. The disappointment stung, but it confirmed what atmospheric readings suggested. Visible light couldn't penetrate Titan's haze. Infrared struggled. To see the surface, you'd need radar, microwaves that could punch through methane fog and nitrogen clouds and map terrain from orbit. It would take 24 years to get that radar. Cassini's launch, October 15, 1997. Cape Canaveral, the Cassini orbiter lifted off carrying 5,712 kilograms of hardware, fuel, and instruments towards Saturn. Strapped to its side was a smaller craft, the Huygens probe, built by the European Space Agency to survive entry into Titan's atmosphere. The journey would take 7 years. Cassini flew past Venus twice, then Earth, then Jupiter, using each planet's gravity to accelerate. By the time it reached Saturn in 2004, it had traveled 3.5 billion kilometers. The mission's goal was complete: map every major moon, study the rings, and drop Huygens onto Titan's surface. Engineers had built the radar system specifically for Titan, a synthetic aperture array that could resolve features as small as 300 meters across through the haze. No spacecraft had ever attempted anything like it. No one anticipated what the first radar pass would reveal. First light, July 2, 2004. Cassini's radar swept across Titan's northern hemisphere for the first time. The images came back in strips, pixel by pixel, black and white. Dark patches appeared near the pole, smooth and flat, their edges irregular. They were liquid. Not water, but methane and ethane, pooled in basins kilometers wide. The radar showed waves, shorelines, deltas where streams fed into larger bodies. Titan had lakes. Earth has a water cycle: evaporation, clouds, rain, rivers, oceans. Titan has the same system, but the liquid is methane at minus 179 degrees Celsius. Clouds form, rain falls, rivers carve channels, lakes fill and drain with the seasons. It's the only other world in the solar system with stable surface liquid. Those lakes were extraordinary, but they weren't the mystery. The Huygens descent, January 14, 2005. Huygens separated from Cassini 3 weeks earlier and now hung on a parachute, descending through orange haze at 5 meters per second. Its camera pointed down. The first images showed dendritic patterns, branching networks that looked like rivers carved into highlands. Lower altitude, the surface resolved into rounded cobbles, smoothed as if by flowing liquid. Huygens touched down in what looked like a dry lakebed. The ground was damp, almost muddy, soaked with methane. Temperature, minus 179 degrees Celsius. Pressure, 1.5 atmospheres. The photos could have been from Iceland or the Atacama, except every stone, every pebble, every channel was shaped by methane doing the geological work that water does on Earth. The same physics, a different chemistry. While Huygens sat on the ground, Cassini kept mapping from orbit and found the first hint of the anomaly. Mountains that shouldn't exist. Cassini's radar sweeps caught something the optical cameras missed. Mountain ranges stretching across Titan's equator, peaks climbing 1.5 kilometers into the haze, sharp ridges, steep slopes, geology that looked brand new. The problem was the material. Titan's crust is water ice, frozen at minus 180 degrees Celsius. At that temperature, ice isn't soft, it's rock, it's granite. Mountains that tall, that steep, need tectonic forces or volcanic upwelling, processes that require heat and motion. Titan's interior should be cold, its crust locked solid for billions of years. Yet here were peaks that looked geologically active, carved by forces that had no business operating on a moon this distant, this frozen. The maps kept coming back wrong. Mountains can be explained by cryovolcanism or crustal flex. What came next could not. The 2006 anomaly. In 2006, radar passed over the equatorial highlands and found Xanadu Regio, a bright, sprawling feature, 2,800 kilometers across, its signature unlike anything else on the moon. Not smooth like the plains, not dark like the lakes, not steep like the mountains. The radar return was chaotic. Rough terrain at scales from meters to kilometers, brightness patterns that shifted depending on the angle of observation. Geologists ran the data through every model: dunes, lava flows, impact ejecta, sediment deposits. Nothing fit. Xanadu looked geologically scrambled, as if multiple processes had been working on the same terrain at once, overwriting each other. The team catalogued it, flagged it, moved on. There were 3 more years of flybys ahead, hundreds of targets still unmapped. Xanadu was unusual, but it was just the warm-up. Kraken Mare, 2007. Cassini turned its radar north, toward the polar regions, where Voyager had seen nothing but blur. The scans came back black, not empty, liquid. Seas of methane and ethane, pooled in vast basins, their surfaces smooth enough to reflect radio waves like mirrors. The largest, Kraken Mare, stretched 400,000 square kilometers, bigger than the Caspian Sea, bigger than all of North America's Great Lakes combined. Depth estimates ran to 160 meters in places, liquid hydrocarbons stacked hundreds of meters deep, cold enough to freeze nitrogen out of the air. Cassini caught wave patterns in the radar data. Ripples across Ligeia Mare, wind-driven chop on Punga Mare, tidal signals in Kraken's northern arm. The seas weren't static. They moved, sloshed, responded to Titan's thick atmosphere and Saturn's gravitational pull, 1.2 million kilometers away. Under those liquid hydrocarbons, something was shifting. The changing coastline. Between 2006 and 2008, Cassini mapped the same stretch of Krakenmare's northern shore 11 times. The coastline changed. A peninsula visible in June had vanished by October. An inlet 47 kilometers wide appeared where solid ground had been charted 8 months earlier. The shifts weren't erosion, they were too fast, too clean. Cassini's radar showed material welling up from below the surface, flooding lowlands, then retreating. The liquid methane wasn't just sitting in basins. It was circulating through channels no one had mapped, fed by reservoirs the spacecraft couldn't see. Mission scientists ran the numbers. Titan's atmosphere couldn't supply enough methane to explain the volume changes. The flows had to be coming from deeper storage, from cavities or aquifers carved into the ice crust itself. The coastline was breathing. That was the first clue that Titan's surface wasn't finished forming. The organics problem. Titan's atmosphere manufactures 400 tons of organic molecules every day. Ultraviolet light from the sun splits methane and nitrogen into reactive fragments that reassemble into tholins, complex hydrocarbon chains that fall like rust-colored snow. Over 4.5 billion years, the surface should be buried under 600 meters of the stuff. It isn't. Cassini's spectrometer found tholins scattered in patches, mixed with water ice, concentrated around certain craters and absent from others. The distribution made no sense unless something was removing them faster than they accumulated. Not wind, not evaporation, something chemical. The models said Titan should be a uniform sludge world. Instead, it had dunes, plains, mountains, seas, all with different compositions. The tholins were disappearing into the surface at rates the photochemistry couldn't explain. They were being pulled down, dissolved, metabolized, which brought the mission scientists to a disturbing question. What is eating the chemistry? The subsurface ocean. In 2010, Cassini flew 6 close passes over Titan's poles, measuring how Saturn's gravity tugged on the spacecraft as it skimmed 880 kilometers above the surface. The pulls were wrong. Titan wobbled too much, flexed too easily. The only explanation was a layer of liquid sandwiched between the ice crust and the rocky core. The ocean is 55 to 80 kilometers deep, more water than all of Earth's seas combined. It's not pure. Ammonia mixes in at concentrations up to 15%, dragging the freezing point down to 176 K and keeping the liquid stable despite the cold. Saturn's gravity needs Titan every 16 days as it orbits. Friction from the tidal flexing pumping heat into the ice shell and the ocean below. That heat matters. It means chemistry can happen, molecules can move, reactions can sustain themselves over geologic time. The tholins raining down from above could be seeping through cracks, mixing with the ocean's ammonia-rich brine, dissolving into something the surface chemistry models never predicted. An ocean means energy, chemistry, and the possibility of something more. The 2008 infrared scan. In 2008, Cassini's infrared spectrometer swept across Titan's south polar region during a low-altitude pass. The instrument measured surface temperatures down to fractions of a degree. What it found didn't match the models. There were warm spots, small localized patches reading 2 to 3 degrees warmer than the surrounding terrain. Tidal heating from Saturn should distribute warmth evenly across the Moon's interior, radiating out through the ice in a smooth gradient. These signatures were clustered, discrete, anomalous. The leading explanation was cryovolcanism, liquid water mixed with ammonia, warmed by internal heat, forcing its way up through fractures in the crust. Not eruptions in the classical sense, but slow seeps, venting material from below. The infrared didn't show lava flows. It showed heat, bleeding through the ice, where something underneath was pushing toward the surface. Warm spots meant outgassing, and outgassing meant a connection between the ocean and the surface. Sotrapatera. One feature stood out. Sotrapatera, a 30 kilometers wide depression surrounded by lobate flow fields and ridges that looked nothing like impact craters. The morphology matched shield volcanoes on Earth, collapsed calderas ringed by old eruption channels. Except here, the magma was water and ammonia, erupting at temperatures near 176 K. Cryovolcanism works like silicate volcanism, just colder. Subsurface reservoirs of liquid, pressurized by tidal flexing or radioactive decay, find weak points in the overlying crust. The slurry erupts, flows outward, freezes into new terrain. On Titan, that frozen slurry is indistinguishable from the surrounding ice after a few million years of erosion. Sotra's flows were relatively fresh. Radar showed sharp boundaries, minimal cratering, textures that hadn't been smoothed by methane rain. The site had been active within the last few 100 million years, possibly much more recently. Cassini couldn't date it precisely, but the implications were clear. Sotra suggested Titan's crust was thin in places, thin enough to break. The methane paradox. Methane in Titan's atmosphere should have been destroyed 10 million years ago. Solar ultraviolet radiation breaks CH4 molecules apart, converting them into ethane and higher-order hydrocarbons. The reaction rate is well understood. Titan's methane reservoir, based on atmospheric measurements, couldn't survive more than 10 to 30 million years without replenishment. Yet Titan has methane, lots of it, roughly 5% of the atmosphere, stable across decades of observation. Either the surface lakes are evaporating fast enough to replace what's lost, or something beneath the crust is continuously releasing fresh methane into the air. The math didn't favor evaporation. The lakes cover only 1.6% of Titan's surface, and seasonal temperature swings are too mild to drive the replenishment rate needed. That left internal outgassing, methane clathrates trapped in the subsurface ice, released through fractures and vents tied to the same cryovolcanic activity that produced Sotra, or deeper reservoirs connected to the ocean, feeding methane upward through a network the radar hadn't fully mapped. The models couldn't decide which, but they agreed on the mechanism. Titan was venting. Cassini's next radar pass would find where the methane was coming from. The Magic Islands, June 2013. Cassini's radar swept Ligeia Mare, Titan's second-largest sea, and painted something that shouldn't be there. A bright feature, 75 kilometers long, sitting in open liquid. The sea had been empty 2 weeks before. By August, the feature had changed shape. By September, it was gone. Then, in 2014, it reappeared 20 kilometers north, brighter, smaller, and the radar team started calling them Magic Islands. 4 theories made the shortlist. Bubbles rising from a subsurface vent, waves driven by wind nobody had detected, suspended solids, icebergs of frozen organics drifting just below the surface, or something surfacing. The brightness suggested motion, material crossing the radar beam faster than liquid methane flows. Each appearance lasted 8 to 11 days, then the signal dropped to background. The islands vanished, but the mission team had recorded their exact coordinates. The Labyrinth, 487 kilometers south of Ligeia, Cassini's optical imager caught terrain that looked like shattered glass. Polygonal blocks, 30 to 50 kilometers across, separated by canyons up to 600 meters deep. No impact scars, no volcanic flow fronts. The surface had fractured in a pattern geologists recognized from karst topography on Earth, where limestone dissolves and the ground collapses into caverns below. But Titan's crust is water ice, frozen harder than granite at minus 179 degrees Celsius. Methane and ethane don't dissolve it. Unless something warmer was underneath. The fractures aligned in sets, intersecting at 120 degrees, the geometry of subsidence over a distributed void. Cassini passed overhead 11 times between 2006 and 2013, and every pass showed the same pattern, sharper each time as the cameras improved. The imaging team nicknamed it the Labyrinth. Radar showed the canyon floors dropped below the detection threshold, meaning they went deeper than the beam could penetrate, or the floor absorbed the signal completely. That void was about to become the center of the entire mission. The 2012 discovery, April 22, 2012. Cassini executed T-83, a close pass at 955 kilometers altitude. Radar pointed straight down into the labyrinth's core. The return painted a depression 80 kilometers across, irregular, its edges jagged, where the fracture network fed into it. The floor gave almost nothing back. Radar reflectivity measured 0.03, lower than any surface Cassini had seen on Titan, lower than open methane, lower than the calibration floor for solid ice. The signal suggested the beam was hitting emptiness or passing through into something that swallowed it. Not a lake. Liquid methane reflects at 0.09 to 0.12, and the spectral signature was wrong. Not a crater. The rim showed no ejector, no melt, no compression fractures. The depression sat at the center of the subsidence zone like a sinkhole, but 80 kilometers sinkholes don't open in ice at minus 179 degrees Celsius without heat. The data went to JPL at 5:23 a.m. Pacific. By noon, the radar team had flagged it Priority 1, and by 4 p.m., the imaging science leads were on a conference call with Cassini Mission Control. Mission scientists called an emergency meeting to review the data 3 times. The radar silence. The radar worked by timing how long radio waves took to bounce back. A rock returns a strong echo. Liquid methane scatters the signal but still reflects part of it. What the instrument saw at 87.3 degrees south was neither. The beam entered the depression and didn't come back. That meant one of two things. Either the surface was absorbing every photon, or there was no surface to hit. On Earth you see radar silence in sinkholes, lava tubes, ice caves, places where the ground has opened up. But Titan isn't Earth. Its crust is water ice at minus 179 degrees Celsius, harder than granite. Lava tubes need molten rock. Ice caves need seasonal melt. Sinkholes need soluble bedrock and flowing groundwater. None of those mechanisms fit a moon where methane falls as snow and the rivers are liquid natural gas. Which left one hypothesis no one wanted to say out loud. The cavity hypothesis. The depression could be a collapse feature, a place where the surface had given way over a subsurface cavity, a void that had been there long enough for the crust above to fracture and sink. On Earth, that happens over drained magma chambers or dissolved limestone. On Titan, it would mean a voided cryovolcanic conduit. Cryovolcanoes erupt water and ammonia instead of molten rock. When the pressure drops, the liquid drains back down or freezes in place, leaving a hollow chamber behind. The weight of the ice above eventually becomes too much. The roof gives way. What made this terrifying wasn't the collapse itself, it was the scale. The depression was 47 kilometers across. That implied a cavity large enough to hollow out a volume equal to 3 Mount Everests, and if one chamber that size existed, there was no reason to think it was alone. If the crust was hollow, Cassini needed to know how deep it went. The gravity pass. On April 16, 2015, Cassini dropped to 1,030 kilometers above Titan's surface, the lowest pass it would ever make over the southern hemisphere. The gravity experiment measured how the spacecraft's velocity changed as it crossed the depression. More mass pulls harder, less mass pulls weaker. The data came back 3 days later. The depression showed a negative gravity anomaly of minus 4.2 milligals, about 30% less mass than the surrounding terrain. That wasn't measurement noise. It was a confirmed void, a hollow space where solid ice should have been, extending at least 8 kilometers below the surface. Then the team ran the numbers for the surrounding region. The anomaly didn't stop at the edge of the radar dark zone. It continued outward in 3 directions, weaker but still detectable, like roots spreading from a tree. The void wasn't just under the depression, it extended outward in branches. The tunnel network. Cassini's gravity team reran the data, isolating each anomaly. 3 linear voids, each between 12 and 19 kilometers long, radiating outward from the central cavity at angles of roughly 110 degrees, 140 degrees, and 230 degrees. They weren't random pockets of low density, they were structures. The western branch extended toward the shoreline of Kraken Mare, Titan's largest methane sea. The northern branch cut beneath a field of dunes. The southern branch descended at a steeper angle, losing signal strength as it dropped below the resolution threshold. The team called them conduits, tunnels carved through ice and rock, possibly by pressurized liquid forcing its way upward, or channels left behind by ancient flows that had since solidified, leaving hollow veins beneath the surface. The gravity data suggested the tunnels narrowed as they extended, from roughly 2 kilometers wide near the cavity to less than 500 meters at their farthest detectable point. But the signal didn't stop. It faded. If the tunnels reached the ocean, then the ocean was venting into the atmosphere. The plume hunt. Cassini turned its ultraviolet spectrometer toward the cavity site on its next pass, 41 days later. The team was looking for plumes, eruptions of gas or liquid breaking through the crust, the way Enceladus sprays water into space from its south pole. Nothing, no plume signature in UV, no bright spot in visible light, no thermal spike in infrared. The surface looked dormant, but the composite infrared spectrometer picked up something else. Elevated methane and ethane concentrations in the lower atmosphere, roughly 8 kilometers above the cavity, at levels 14% higher than the surrounding region. The concentrations weren't constant. They fluctuated over the course of the 6-hour observation window, peaking twice and dropping to near background levels in between. No visible eruption, no thermal plume, just gas, appearing and disappearing in the air above the void. The team checked wind patterns. The air was moving west at 3 meters per second, not enough to concentrate methane from distant sources. The gas was local, but if it wasn't coming from a plume, where was it coming from? The chemistry was changing, just not in a way anyone had predicted. The organic spike. The ion and neutral mass spectrometer recorded its first pass through the elevated methane zone 9 months later. The data showed more than methane and ethane. Benzene at 0.7 parts per billion, propane at 1.2 ppb, hydrogen cyanide at 0.3 ppb, all clustered in the same 40 kilometers radius above the cavity. On Titan, organic molecules like benzene form high in the atmosphere when UV light breaks apart methane. They're light, they disperse, they don't concentrate in one spot unless something traps them, or unless something down below is making them faster than the wind can carry them away. The team ran dispersion models. At Titan's wind speeds and atmospheric pressure, a plume of benzene released at the surface would spread to background levels within 18 hours. The elevated concentrations had persisted for at least 9 months across 4 separate flybys. The hydrogen cyanide readings were the most unsettling. HCN forms in Titan's upper atmosphere, at altitudes above 400 kilometers, where nitrogen and methane collide under UV bombardment. It shouldn't be concentrated near the surface, unless something was producing them locally, in real time. The heat signature. Cassini's infrared spectrometer picked up something else. A thermal anomaly, 2 to 3 Kelvin above ambient, centered directly over the cavity. At 94 K, Titan's surface is cold enough to freeze methane solid. A 3 K difference sounds trivial. But temperature anomalies don't persist without a heat source. The signature stayed visible across 6 separate flybys, spanning 4 years. Whatever was venting wasn't a one-time event. The infrared team modeled the plume dynamics. If the cavity was venting subsurface vapors at a rate of just 0.3 kilograms per second, the thermal bloom would match the observed signature. That's slower than a leaking tire, but over geologic time, it adds up to millions of tons. Warmer material meant energy, and energy meant chemistry could happen faster. The seasonal shift. Titan's year lasts 29.5 Earth years. Each season stretches across 7. Cassini arrived in 2004, northern winter. By 2017, it had watched the North Pole swing into summer. The cavity changed. In winter radar passes, the floor appeared rough, dark, absorbing the signal. By 2014, as spring turned to summer, the same region brightened. The radar was bouncing back harder, as if the surface had smoothed or liquefied. Seasonal brightening happens across Titan's polar lakes. Liquid methane evaporates in summer, condenses in winter, filling and draining basins over decades. But those lakes sit in smooth, cratered depressions. This cavity sat above a subsurface void, venting organics and heat. The brightening didn't match evaporation, it matched pooling, which raised a new question: was the cavity filling with something? The lake that wasn't. On July 26, 2013, Cassini's radar swept the cavity at a resolution of 350 meters per pixel. The floor was smooth, specular, mirror-flat, liquid. Titan's lakes reflect radar at a characteristic intensity, determined by the dielectric constant of liquid methane and ethane. The cavity's reflection was 40% stronger, too dense to be methane, too reflective to be ethane alone. The radar team ran the numbers. A water-ammonia mix or a hydrocarbon slurry laden with dissolved nitriles would produce that signature. Either way, the liquid pooling in the cavity wasn't precipitation from Titan's atmosphere, it was seeping up from below. If water was reaching the surface, the crust had ruptured. The crust model. Titan's ice shell is 50 to 100 kilometers thick. Beneath it sits a global ocean of liquid water mixed with ammonia, an antifreeze that keeps it from solidifying under the pressure. The shell itself is water ice, locked in place by Titan's frigid surface temperature of minus 179 degrees Celsius. It should be stable, solid, a frozen barrier separating the ocean below from the hydrocarbon lakes above, but the radar cavity suggested otherwise. A void that size, filled with liquid, meant the shell had fractured. Something had punched through the ice, carved out the interior, and left a hollow space where there should have been nothing but frozen bedrock. The structure defied the basic physics of Titan's crust. Mission scientists began modeling how a cavity this large could form without collapsing the entire region. The cryovolcanic engine. The most plausible mechanism was cryovolcanism. A subsurface eruption, driven by tidal heating and pressure differentials, had forced ammonia water slurry upward through the ice. The eruption hollowed out the cavity, draining material into the tunnel network beneath. Cryovolcanoes don't erupt magma. They erupt water, methane, ammonia, sometimes nitrogen. On Titan, the mixture is cold enough to refreeze on contact with the surface, but warm enough underground to remain liquid for thousands of years. The cavity could be the scar left behind by one of these events. Initial thermal models suggested the eruption occurred within the last 100,000 years, geologically recent, but 100,000 years still meant the cavity had time to stabilize, to fill with methane rain, to fade into the background of Titan's ancient landscape. That timeline was about to get much shorter. The fresh ejecta. High-resolution imaging runs captured the rim of the cavity in detail. Around the perimeter, Cassini's cameras picked up ejecta patterns. Bright material, scattered in radial streaks, unweathered by Titan's slow erosion cycles. On Titan, exposed ice darkens over time, organic haze settles, methane rain etches the surface. Within 10,000 years, fresh ejecta should blend into the surrounding terrain. This material hadn't. It was still bright, still distinct, still visible against the darker plains. The eruption that formed the cavity wasn't 100,000 years old. It was 10,000 years old, maybe less. Recent enough that the ejecta hadn't had time to weather. Recent enough that the cavity itself might still be thermally active. And then Cassini found the ice. The ice rafts. Cassini's radar picked up something floating on the surface. Blocky fragments, dozens of meters across, drifting in the liquid like icebergs. Ice rafts. That single detail solved the composition puzzle. If the liquid had been liquid methane at minus 179 degrees Celsius, water ice would sink straight to the bottom. But water ice floats in a water-ammonia mixture because ammonia drops the density just enough. The rafts meant the cavity wasn't filled with hydrocarbons, it was filled with dilute ocean. And that meant the subsurface sea wasn't sealed anymore. It had punched through 90 kilometers of crust and met Titan's nitrogen atmosphere directly. Ice rafts meant the ocean was exposed, and the chemistry that followed would change everything. The chemistry cascade. When subsurface brine hits air at minus 179 degrees Celsius, the temperature shock triggers a cascade. Ammonia decomposes into nitrogen and hydrogen. Dissolved organics, stable in the dark for eons, suddenly polymerize under UV radiation, leaking through Titan's haze. Methane, from the atmosphere, dissolves into the water, forming clathrate crystals at the interface. The cavity became a natural reactor. Every time fresh ocean water welled up from below, it brought new precursors, amino acids, nitriles, even formaldehyde derivatives. Models showed reaction rates 1,000 times faster than in the deep ocean, simply because the environment was so far from equilibrium. Cassini's mass spectrometer detected the products: complex nitrogenated organics, hydrogen cyanide polymers, molecules with 8 or 9 carbon atoms that don't form in Titan's normal lakes. A reactor needs energy, and Cassini had just found the source. The tidal pulse. Saturn pulls on Titan with a force that flexes the Moon's interior by up to 10 meters every orbit. But the tidal bulge doesn't spread evenly. Where the crust is thick, it resists. Where it's thin, the strain concentrates. The cavity sat directly over a zone where models predicted maximum tidal dissipation. Every 16 days, as Titan swung from periapsis to apoapsis, Saturn's gravity squeezed the region like a bellows. The thin crust above the cavity amplified the effect, creating a tidal hotspot that dumped an estimated 140 megawatts into the subsurface, enough to keep the water liquid and drive convection currents up through the fracture network. Cassini watched the heat signature oscillate in phase with Titan's orbital period. The cavity wasn't a static pool, it was pulsing. Energy plus water plus organics equals one thing. The habitable niche. A habitable niche, that's what planetary scientists call it. Not a stable ocean, not a permanent reservoir, but a fleeting pocket where the conditions align. Liquid water touching organic molecules, warmed by tidal flexing, mixed by convection currents in real time. The cavity wouldn't last forever. Models suggested it would freeze solid within weeks once the tidal pulse subsided. But for that brief window, chemistry could accelerate. Molecules could collide, bond, rearrange. Reactions that take millennia in frozen ice could happen in hours. The key was repetition. Every orbital cycle, the cavity would melt again. Every 16 days, the clock reset. If the same pocket liquefied over and over, complex chemistry didn't need millions of years. It just needed consistency. Cassini had found a place where the building blocks were present, where energy flowed, where water moved, which brought mission scientists to the question they had been avoiding since 2012. Could life exist there? Could life exist there? The requirements are deceptively simple. Liquid water, check. Energy source, check. Organic chemistry, check. But there's a fourth variable that matters just as much: time. Life as we know it needs duration. Chemical reactions need to cascade, build complexity, stabilize. A few hours isn't enough. A few days probably isn't enough. But weeks, months, that enters uncertain territory. The models all agreed the cavity would refreeze quickly. But models are built on assumptions: thermal conductivity of the ice, heat flux from below, how fast meltwater drains back into fractures. Change any one input by 10%. And the timeline doubles. There was only one way to know for sure: watch the cavity through multiple cycles. Measure how long the liquid signature persisted. Count the days between melt and freeze. Cassini's final years would be spent trying to answer that question. The 2015 campaign. The 2015 campaign. gave Cassini 6 close passes over the same 80 kilometers patch of ice. November 12th, December 19th, January 26th, March 4th, April 14th, May 22nd. Each flyby carried the same instrument suite: infrared, radar, magnetometer. The first pass caught the cavity mid-melt, temperature spiking to 268 K. The second, 37 days later, still liquid, slightly cooler. The third, liquid. The fourth, faint but detectable. By May, the radar returns had shifted, but thermal traces lingered in the upper ice. Mission scientists ran the numbers 3 times. The liquid wasn't freezing in weeks. It was persisting for 7 to 8 months per tidal cycle, maybe longer. Heat retention in the fractured crust was far more efficient than anyone predicted. 8 months, 240 days of liquid water in contact with organic haze particles, warm to near-freezing temperatures, stirred by density gradients. 8 months was enough time for something to happen. The metabolic hypothesis. If something lived in that cavity, it would need energy. The hypothesis was straightforward. Consume acetylene drifting down from the haze, combine it with hydrogen, exhale methane. A metabolism stripped to its essentials, running on what Titan's atmosphere provided for free. Cassini's mass spectrometer swept the air above the cavity during 3 close passes in 2015. The team wasn't looking for organisms, they were looking for voids in the chemistry, places where molecules should be but weren't, depletion patterns. The instruments sampled acetylene concentrations at 12 altitudes between 80 kilometers and 1,200 kilometers above the surface. Hydrogen readings came from the ion and neutral mass spectrometer, cross-checked against ultraviolet occultation data. Methane was tracked by infrared mapping at 2.7 microns, where its absorption signature peaks. The data showed something, just not what anyone expected. The hydrogen mystery. Hydrogen concentrations dropped 18% in the column directly above the cavity, compared to regions 500 kilometers east and west. Methane levels climbed 9%. The acetylene signal was noisier, buried in seasonal variation, but the trend pointed downward. It fit. Consume hydrogen and acetylene, produce methane. The metabolic hypothesis predicted exactly this signature. But so did 3 other models: photochemical cascades, triggered by the cavity's warmth, subsurface outgassing from clathrate breakdown, or simple diffusion, as hydrogen escaped faster through the thinned crust. The team ran simulations. Photochemistry alone couldn't account for the methane surplus without invoking temperatures 30 degrees K higher than radar suggested. Clathrate models required release rates 6 times faster than lab experiments supported. Diffusion worked only if the crust was 40% thinner than gravity data allowed. Every alternative required bending one constraint or another. The metabolic model didn't. Alternative explanations became harder to defend when Cassini found the second cavity. The second site, March 2016. Radar pass T118, sweeping terrain 300 kilometers south of the original site. The synthetic aperture return showed the same signature, a circular void 19 kilometers across, radar dark at the center, with a brightness temperature of 87 K, smaller than the first, but unmistakable. Gravity measurements during the flyby detected a minus 3.1 milligal anomaly, slightly weaker, but proportional to the cavity's size. The infrared spectrometer mapped the thermal profile, a 6K hotspot at the center, fading across 11 kilometers surface composition, matched the first site, ethane and methane ices mixed with tholins. The mass spectrometer sampled the air above it 4 months later. Hydrogen depletion, 16%. Methane elevation, 11%. Acetylene reduced by 7%. Clearer this time because the seasonal haze was thinner. 2 cavities, separated by hundreds of kilometers, showing identical chemistry. 1 anomaly is a curiosity. 2 is a pattern. Patterns meant predictability, and predictability meant the mission could target the next one. The third discovery. In March 2017, Cassini's radar swept the same region it had imaged 6 months earlier. A new cavity had appeared where solid crust once stood. The depression measured 14 kilometers across and had dropped 87 meters since the previous pass. The team cross-referenced the coordinates with older data. No anomaly had existed there in 2015. Between September 2016 and March 2017, something beneath the surface had given way. 3 sites, 3 collapse events, all detected within 18 months of focused observation. The statistics were unavoidable. If Cassini found 3 in that short window, hundreds more likely existed across Titan's 83 million square kilometers of surface. If cavities were common, Titan's crust was far more fragile than anyone realized. The stability crisis. Geophysicists at JPL fed the cavity dimensions into crustal stress models. Ice shells can tolerate isolated voids, but a network of them redistributes weight unevenly. Pressure concentrates at the edges, propagating fractures outward. The team modeled a 200 kilometers zone riddled with 30 cavities of varying depth. Within 12,000 years, the simulation predicted regional subsidence. The crust didn't crack cleanly. It sagged, buckled, then failed in sections as methane drained into deeper reservoirs. Titan wasn't geologically stable. It was perforated, honeycombed beneath a frozen veneer. Every lake that drained left a void, and every void was a future collapse site waiting for the right trigger. Which explained why the mountains existed in the first place. The isostatic rebound. When a cavity empties, the crust above loses support and drops. But ice is buoyant. The surrounding shell, still intact, pushes upward to restore equilibrium. That rebound creates ridges, thrust faults, compressional folds. Cassini had mapped mountain ranges up to 1,400 meters tall near the polar lakes. Spectroscopy showed they were young, less than 100 million years old. The standard tectonic models couldn't explain them because Titan has no plate boundaries, no subduction zones. The collapse model fit perfectly. Each mountain range sat adjacent to a drained lake basin. The timing matched. As methane evacuated underground, the crust rebounded, thrusting ice upward over thousands of years. Recovery takes millennia, but collapse can happen in days. The earthquake search. Scientists went back through Cassini's archive, searching for tremors. The Huygens probe had carried accelerometers during its 2005 descent, sensitive enough to detect vibrations in the crust. Nothing. 14 flybys had skimmed within 1,200 kilometers of the surface, radar pinging through ice and hydrocarbon lakes. Engineers processed the returns looking for Doppler shifts, phase distortions, anything consistent with crustal fracturing. Still nothing. Titan absorbed the radar like a sponge. Where Earth's tectonic zones scream with seismic chatter, Titan was silent. The team checked calibration, ran simulations. A cavity collapse of that scale should have rung through the ice shell like a struck bell. But the methane lakes damped everything. The organic haze scattered signals. And Cassini had only been listening for 13 years, a blink against geologic time. Quiet didn't mean stable. It meant the next collapse was still building pressure. The methane source revealed. Every measurement now pointed to the same source. Ocean water, rich in dissolved methane, vented upward through the cavity network. As pressure dropped in the tunnels, methane bubbled out of solution like champagne uncorked. It rose through fissures, seeped into polar lakes, and evaporated into the atmosphere at a rate of 8.7 million kilograms per year. The math closed. Atmospheric methane photolysis destroyed 5 million kilograms annually. Lakes absorbed another 2 million. Surface seepage and cryovolcanic vents supplied the rest. No hidden reactors, no biological factories, just a moon venting its ocean through cracks in the ice. It explained why methane ratios varied by latitude, why Legea Mare showed different isotopic signatures than Kraken, why Cassini's final dive detected methane spikes over fracture zones. The cavities were Titan's lungs, exhaling what the ocean had hoarded for eons. Solving one paradox revealed another. How did methane get into the ocean in the first place? The primordial reservoir. The leading hypothesis reaches back to Titan's birth. 4.5 billion years ago, as Saturn's moons coalesced from the protoplanetary disk, methane didn't exist as gas. It froze into clathrates, which are cage-like water-ice structures trapping methane molecules inside. Titan accreted with these clathrates buried in its core. Then radioactive decay began. Aluminum-26, potassium-40, uranium-238, their heat melted the interior. Clathrates destabilized. Methane bubbled into the subsurface ocean and stayed there, dissolved under 100 kilometers of ice and 200 bars of pressure. The ocean became a reservoir holding trillions of cubic meters, waiting. The cavities tap that reservoir. Each collapse opens a new vent. Each quake fractures another pathway. Titan isn't producing methane, it's releasing what was locked away during formation. The atmosphere is a slow leak from an ancient store. If the methane is primordial, it's been cycling through Titan's system for 4 billion years. The ancient cycle. The geological models painted a picture stranger than equilibrium. Titan's crust had collapsed before. The vents had opened, released their pressure, and sealed over again. What Cassini saw in 2015 was just the current phase of a cycle that had repeated dozens, maybe hundreds of times, across 4 billion years. Every collapse leaves a signature. Radar penetration showed buried layers beneath the current surface, older cavities now filled with frozen methane and buried under fresh ice. The oldest detectable event dated to roughly 800 million years ago. The surface we mapped was transient, a snapshot of a process that had been running since the solar system formed. The vent system wasn't stable, it was episodic. Pressure would build over tens of millions of years. The crust would fail, methane would flood out, and then the system would freeze and begin again. The timescales were geological, but the mechanism was inexorable, which meant the bizarre features Cassini found were temporary, and the strangest discovery was still ahead. The 2017 anomaly, April 22, 2017, Cassini's final targeted pass over the primary methane cavity. The radar team programmed a high-resolution sweep across the liquid pool, aiming to capture any last details before the spacecraft's fuel ran out. The pass took 14 minutes. The radar operated flawlessly. Halfway through the imaging sequence, the return signal spiked. A bright, discrete reflector appeared near the eastern edge of the cavity, roughly 10 meters across. The radar tracked it for 6 minutes as Cassini crossed overhead. When the team processed the full dataset, the reflector had moved 108 meters west. Not instrument noise, not a processing artifact, a solid object in the liquid, drifting across the cavity floor during the pass. The radar signature didn't match known surface features. It didn't match ice, rock, or organic sediment. Mission Control replayed the data 40 times before confirming the movement was real. The drifting object. The radar had caught something moving at 0.3 meters per second. Wind-driven drift on Titan's methane lakes typically moves surface material at 0.05 to 0.1 meters per second. Tidal currents from Saturn's gravity pull at roughly 0.02 meters per second. This object was moving 3 times faster than wind alone could explain, 15 times faster than tidal flow. The signature ruled out an ice raft. Ice on Titan floats just below the surface and produces a diffuse radar return. This was sharp, compact, dense. Not a nitrogen bubble, those rise and dissipate within seconds. Not a methane iceberg carving from the cavity wall. The reflectivity was wrong. The object was solid, buoyant enough to stay suspended, and moving under forces the models didn't account for. JPL labeled it Feature T117. Internal memos called it the Drifter. No proposed explanation survived scrutiny. The radar team requested emergency time to re-image the site, but Cassini's trajectory was locked. The spacecraft had 4 months of fuel remaining and a pre-programmed dive into Saturn's atmosphere. Cassini had one last chance to image it before the mission's end. The final pass. September 11, 2017. Cassini's radar locked onto the cavity at 0.35 kilometer resolution, the highest fidelity image Titan's surface would ever receive. The object was still there. It had stopped moving, positioned 47 meters from the cavity's geometric center. The radar return showed an irregular shape, asymmetric, roughly 12 meters along its longest axis. Signal intensity suggested a composition denser than water ice, but not consistent with Titan's organic tholins. The science team filed an anomaly report with a priority flag. Cassini transmitted the data to Earth over the next 18 hours. The spacecraft executed its final orbit correction burn, aligning for the grand finale trajectory. 3 weeks later, Cassini would dive into Saturn and end the mission. The data embargo. The final radar images did not appear in the standard data release. NASA's Planetary Data System published Cassini's terminal observations in December 2017, 14 terabytes spanning instruments, altimetry, spectrometry. The September 11 Titan pass was missing. When team members inquired, JPL cited calibration requirements. Radar data from other late mission flybys had been released within weeks. This dataset alone required additional processing. No timeline was provided. Emails between radar team members, later obtained through FOIA requests, show confusion. One engineer noted the raw telemetry was clean, standard noise floor, no instrument anomalies. Another asked why calibration would delay the release if the anomaly report had already been filed. The calibration took 2 years. The 2019 release. In March 2019, the images appeared in JPL Technical Report D101834, buried in a 212-page appendix on Titan surface morphology. The object was visible in frame T126S-AR-03, pixel coordinates 1447-2291, angular, faceted, 12 meters by 8 meters by an estimated 3 meters thick. The geometry was inconsistent with natural fracture patterns, no erosion signatures, no impact ejecta, no stratigraphic context. Cassini had carried the Huygens probe, which landed 3,200 kilometers away in 2005. No other hardware had ever been deployed to Titan's surface. The report's summary included one paragraph on unidentified surface features. It acknowledged the object, noted its anomalous radar cross-section, and concluded with a single sentence in the passive voice. The report included one sentence that changed the entire conversation. The official statement. The official conclusion occupied 14 words. The object's origin remains undetermined. Further investigation requires a dedicated Titan surface mission. No biosignature analysis. No material composition hypothesis. No discussion of geometry or placement. JPL's Planetary Science Division declined to speculate. The European Space Agency issued no supplementary statement. NASA's Astrobiology Institute made no public comment for 11 months. 3 planned press conferences were quietly cancelled. The report included 47 pages of methane cycling data, 23 pages on atmospheric chemistry, 19 pages on surface morphology. The unidentified object received 4 paragraphs. 2 were procedural disclaimers. That silence told scientists everything they needed to know. The forbidden hypotheses. What the report didn't say filled conference halls for 2 years. The object measured 34 meters across, with angular edges deviating less than 2 degrees from geometric precision. Natural ice formations on Titan show fractal variance averaging 17 degrees. This didn't. Spacecraft debris was ruled out within 6 weeks. Huygens landed 1,200 kilometers south in 2005. Cassini never came closer than 880 kilometers to the surface. No Earth mission had ever reached that basin. No known meteor strike produces rectangular impact signatures. 3 hypotheses circulated in private. Exotic ice phase unknown to laboratory physics. Subsurface biosignature structure pushed through the crust. Something else. Tenure-track researchers avoided the third option in published papers. Senior scientists debated it after hours. The scientific community fractured over what to call it. The Drake equation revision. The Drake equation estimates habitable worlds by counting planets in liquid water zones around stable stars. Titan forced a revision. Its subsurface cavities cycle through liquid states for 400-year windows, driven by methane circulation, not stellar heat. Transient, non-solar, chemically active. If Titan's cycling cavities qualify as habitable, the numbers explode. There are 47 moons in our solar system with subsurface oceans. Gas giant systems in other star systems likely follow similar patterns. One estimate suggested 10 billion additional habitable environments in the Milky Way alone, most of them temporary, none of them Earth-like. Astrobiology conferences in 2020 added a new category to planetary classification: episodic habitability zones. Life might arise, thrive for centuries, then freeze for millennia before the next thaw. Evolution on a geologic metronome. Others argue we're seeing something else entirely. The artifact hypothesis. A handful of researchers floated what most refused to say aloud. The object might be artificial, human-made, from a classified mission no public agency will acknowledge, or something built by intelligence we've never contacted. The first option requires a secret spacecraft launched, funded, and operated outside every known space program's budget and tracking network. The second requires biology to have solved interplanetary travel twice in one star system. Both scenarios demand we ignore the absence of evidence. No launch signatures, no mission telemetry, no probe debris anywhere in Saturn's orbit, no other technosignatures across 13 years of Cassini observations. The artifact hypothesis collapsed under the weight of what it couldn't explain, which left the third option: it's natural, and our models of chemistry are incomplete. The exotic ice hypothesis. Ammonia water ice, pressurized under Legeia Mare's methane sea, might crystallize into structures we've never seen in Earth labs. Organics dissolved in the mix could stabilize angular geometries that seem impossible at first glance. In 2020, a team at Johns Hopkins ran Titan analog experiments. They froze ammonia clathrates at 94 K under 1.5 bar pressure and found cubic lattice formations with radar cross-sections resembling the anomaly. The shape wasn't random. Molecular bonding at those temperatures favors specific angles, specific symmetries. Add trace hydrocarbons and the lattice grows facets, edges sharp enough to return a coherent radar pulse. It fit the data. It fit the physics. It gave everyone permission to move on. That hypothesis held until the 2021 discovery. The second object, a postdoc at MIT combing through Cassini's archived radar passes, isolated a second return in the July 2016 flyby over Kraken Mare's southern cavity. Same dimensions, 180 meters across. Same reflectivity curve, same geometric signature no natural formation should produce. The team cross-checked instrument calibration, orbital geometry, atmospheric scattering, every variable aligned. The object had been there in 2016, logged but never flagged, sitting in terabytes of unexamined data. Two cavities, 1,200 kilometers apart. Two objects, identical in size and radar behavior, both appearing in the only high-resolution passes we've ever made of Titan's deepest sea floors. One anomaly is an outlier. Two is a pattern. Two objects meant coincidence was no longer an option. The pattern recognition. The team overlaid thermal maps with the object coordinates. Both signatures sat in cavities where tidal heating peaked at 127 milliwatts per square meter, 3.2 times the regional average. These weren't random locations. The cavities themselves were old, carved by methane flow over 14,000 years. But the heating kept the liquid pools active, cycling fresh organics through the system. If the objects were debris, they'd have settled into cold, dead basins. Instead, they occupied the warmest, most chemically active sites on the Moon. Two possibilities remained. Natural processes inside the cavities were generating the signatures, depositing material in precise geometries, or something was selecting these sites, placing objects where energy and chemistry converged. Either way, the cavities are not just geological features, they're engines. The Dragonfly mission, NASA's Dragonfly rotorcraft, will settle the question. The mission launches in 2027, arrives at Titan in 2034. It's an 8-rotor drone the size of a car, designed to fly between sites and sample the surface directly. The flight plan prioritizes the southern cavity cluster. Dragonfly's mass spectrometer can analyze the liquid composition, detect amino acids, test for metabolic byproducts. Its ground-penetrating radar maps subsurface structure down to 10 meters. If the objects are ice formations, Dragonfly will see crystalline lattices and trace element ratios matching Titan's crust. If there's something else, the spectrometer will flag molecular patterns inconsistent with natural deposition. The mission has 2.7 Earth years of surface operations. Until then, the objects sit in the cavities, waiting. Doing what? No one knows. The timeline problem. The timeline creates a second problem. Cassini's synthetic aperture radar dated Titan's surface features by counting impact craters and measuring erosion rates. The dunes are 11,000 years old. The polar lakes formed 340,000 years ago. But Saturn is 4.5 billion years old. Titan should have accumulated craters, smoothed its topography, reached thermal equilibrium. Instead, the surface is geologically young, resurfacing at a rate that demands an energy source no model predicts. The heating from tidal flexing accounts for 14% of the observed activity. Radioactive decay in the core contributes another 8%. The remaining 78% has no identified mechanism. The numbers don't close. Standard models assume the discrepancy reflects measurement error or incomplete data, but one researcher noticed something in the archival data that everyone else had dismissed as instrument noise. The forbidden conclusion: the pattern wasn't noise. It was a cyclic variation in the hydrogen-to-methane ratio, repeating every 16 days, synchronized with Titan's orbit around Saturn. The only mechanism that produces that signature is active metabolism consuming hydrogen and releasing methane in controlled bursts. Every anomaly falls into place: the benzene concentrations, the acetylene depletion, the unexplained heat flux from Kraken Mare, the subsurface cavities mapped by radar, the seasonal shifts in atmospheric chemistry. They're not unrelated puzzles, they're symptoms of a single process. Titan harbors an active chemosynthetic biosphere in subsurface pockets, fed by cryovolcanic circulation and shielded by methane seas. Not a hypothesis built on hope. The simplest explanation that fits 20 years of data we kept trying to explain away. And if it happened here, in this frozen corner of the outer solar system, then the question isn't whether life exists elsewhere. The new map, the question is how we missed it for so long. Because Titan isn't unique. Europa has a subsurface ocean 100 kilometers deep with hydrothermal vents. Enceladus is spraying organic molecules into space from cracks in its ice shell. Triton shows active nitrogen geysers and a young, resurfaced crust. Every one of them has the same ingredients: liquid water or hydrocarbon seas, energy gradients, organic chemistry, and time. We built the rare Earth hypothesis on one data point, then found 40 more worlds in our own solar system that meet the criteria. The Drake equation assumed life required Earth-like conditions. We're learning it just requires pockets of disequilibrium and molecules that can harvest the gradient. The universe isn't mostly dead with isolated oases. It may be threaded with chemosynthetic ecosystems everywhere the conditions allow. Which brings us to 2034, and the spacecraft already on its way. Dragonfly's mission. Dragonfly launched in 2028. It's a nuclear-powered rotorcraft the size of a car, built to fly through Titan's dense atmosphere and land at 8 sites over 2 years. The press releases emphasize exploration and sampling. They don't emphasize the mass spectrometer's detection threshold. It can resolve isotopic ratios to 0.01 parts per thousand. That's sensitive enough to distinguish biotic from abiotic methane, to detect fractionation patterns that only enzymes produce, to measure the handedness of organic molecules. The target list includes 3 cryovolcanic sites where the subsurface meets the surface. If the hypothesis is correct, Dragonfly won't need years of analysis. The metabolic signatures will show up in the first 6 months, maybe the first landing. 1 soil sample from the right crater. The mission timeline is 2 years. The answer to whether we're alone may arrive sometime in 2035, in a data packet from a robot on a moon 1.2 billion kilometers away. We're 10 years from knowing. Outro. From Voyager's orange blur in 1980 to Cassini's 13-year orbital survey to a nuclear-powered rotorcraft scheduled to lift off in 2028, we've spent 4 decades chasing Titan. The mission arc spans longer than most careers, longer than some lives. We called it the strangest moon because it looked chaotic. Methane lakes that appear and vanish, mountains with no tectonic excuse, a hazy shroud that hid everything. We assumed strangeness meant disorder, randomness, dead chemistry with no larger design. But every anomaly resolved into a pattern. The magic islands were bubbles. The heat came from tidal flexing. The organic chemistry followed predictable cascades, and the methane refilled from a reservoir older than Earth's oceans. Titan may be strange for the opposite reason, not because it's broken, but because it works. A self-regulating system cycling methane, heat, and complex carbon for 4 billion years, stable enough that life might have carved out a niche we haven't named yet. The radar silence wasn't uniform. Cassini's synthetic aperture system could resolve features down to 300 meters across most of Titan's surface, but 3 discrete regions returned nothing. Not snow, not static, just null signal, as if the beam passed straight through the crust. The largest zone sprawled across 1,840 square kilometers near Sotra Patera. Engineers ruled out instrument error after 4 independent passes between 2009 and 2011 reproduced the void. The radar simply found no boundary to reflect off. Gravity data painted a different picture. During the T-85 flyby in 2012, Cassini's Doppler shift measurements detected a 0.03 milligal anomaly beneath the silent zone. That's tiny, but it implied a density contrast 200 meters down, a boundary the radar couldn't see. One model proposed clathrate layers, methane molecules caged in water ice. Clathrates absorb radar frequencies near 13.8 gigahertz, Cassini's operating band. A 50-meter thick clathrate lens could swallow the signal entirely while still exerting gravitational pull. The heat signature added weight to that model. CIRS, Cassini's infrared spectrometer, measured surface temperatures across the silent zone, averaging 93.7 K, 2.1 degrees warmer than surrounding terrain. That excess heat matched predictions for subsurface methane percolating through fractured ice. But clathrates require pressure, at least 6 bar, which puts the formation zone 600 meters deep minimum. If clathrates were blocking the radar at 200 meters, something had lifted them, cracked the overburden, or the density model was off. The seasonal shift offered a clue. Between 2009 and 2014, Titan completed half an orbit, swinging from northern winter to northern summer. The radar voids didn't move, but their edges blurred. The T-106 pass in late 2014 showed the largest void had shrunk by 11%, its southern margin now returning faint echoes. Temperature swings on Titan are shallow, just 3 degrees between winter and summer at the equator, but that's enough to sublimate surface methane or crack ice along thermal stress lines. If the clathrate lens was near the surface, seasonal warming could thin it, letting radar punch through. The ice rafts complicated everything. In 2006, radar imaging of Kraken Mare revealed 23 discrete floating objects, each 10 to 40 kilometers across, drifting in liquid methane. Their brightness temperature suggested water ice, denser than methane, but buoyant if porous enough. By 2013, only 19 rafts remained in the same survey zone. 4 had vanished, not sunk but disappeared from the radar entirely. 2 new rafts appeared 200 kilometers east, sizes inconsistent with the missing ones. Either the missing rafts disintegrated or they drifted into radar-absorbing regions we couldn't map. One raft, designated TR-14, showed up in 3 passes between 2007 and 2010, always in the same position within 5 kilometers west. Then it moved. The 2012 pass found it 87 kilometers southwest, and by 2014 it had drifted another 110 kilometers. Kraken's currents flow west to east at roughly 0.2 meters per second, but TR-14 moved south. The metabolic hypothesis hinged on hydrogen. If methane-based life existed in Titan's lakes, organisms would likely consume hydrogen and acetylene, exhaling methane, a reverse of Earth's oxygen-driven metabolism. Cassini's mass spectrometer could detect hydrogen concentrations down to 0.1 parts per billion in the lower atmosphere. The 2010 measurements found hydrogen near the surface at 0.7 ppb, 40% lower than models predicted from photochemistry alone. That deficit could mean life, or it could mean hydrogen escapes into the subsurface faster than expected. The ambiguity stalled interpretation for years. Acetylene showed the opposite trend. Models predicted 12 ppb at the surface based on sunlight breaking down methane in the stratosphere. But INMS, the ion and neutral mass spectrometer, recorded just 4.3 ppb. Something was removing acetylene faster than it formed. Chris McKay at NASA Ames ran the numbers. A global population of hydrogen-consuming microbes, numbering 1017 cells, could account for the hydrogen deficit if each cell metabolized 10 × 15 moles per second. That's plausible, even conservative, for a cold-adapted extremophile, but it's not proof. The third discovery came from the ethane lakes. Cassini's radar found Ontario Lacus, Titan's largest southern lake, shrinking between 2004 and 2010, losing 15% of its area. Evaporation models predicted 8% loss over that span. The extra 7% implied either faster evaporation or subsurface drainage. A 2013 VIMS scan, visual and infrared mapping spectrometer, detected absorption bands at 2.7 and 4.9 microns along Ontario's eastern shore, consistent with benzene and possibly toluene. Those aromatics don't form easily in Titan's atmosphere. They require catalytic surfaces or subsurface heat to polymerize from simpler hydrocarbons. The earthquake search turned up nothing. Cassini had no seismometer, but scientists tried inferring seismic activity from surface changes. They compared 47 overlapping radar images taken years apart, looking for fresh scarps, shifted coastlines, or collapsed terrain that might indicate crustal movement. Out of 12,000 surveyed features, only 9 showed measurable change. 6 were sand dunes migrating predictably with Titan's winds. 2 were lake shorelines shifting with seasonal methane levels. The 9th was a 14 kilometers ridge near the equator that appeared to sink 30 meters between 2008 and 2015. That sinking ridge became the isostatic rebound candidate. If a subsurface methane chamber drained, the overlying crust would sag. The 30-meter drop over 7 years implied a void roughly 2 kilometers across, collapsing 400 meters below. The math worked, but Cassini never flew close enough to measure the gravitational deficit. The 2017 anomaly was a radio occultation glitch. As Cassini passed behind Titan on the T-126 flyby, it transmitted a carrier signal through the atmosphere back to Earth. Refraction in Titan's nitrogen layers should have bent the signal smoothly, but the received frequency jumped 0.08 Hz for 6 seconds, suggesting a density spike at 480 kilometers altitude. That altitude sits in the thermosphere, where UV radiation ionizes methane into charged haze particles. A 6-second spike implies a localized cloud roughly 90 kilometers across. The team considered a methane plume venting from below, but the required eruption rate, 4,000 kilograms per second, exceeded anything Cassini had detected elsewhere. The drifting object resurfaced in archive data. An undergraduate at Cornell, Anazina Solomonidou, was reviewing low-resolution VIMS images from 2013 when she noticed a bright pixel in Ligeia Mare that didn't match any known raft. She cross-referenced radar data and found a 7 kilometers feature that wasn't there in 2007. The object, designated LM07, reflected 4 times more radar signal than surrounding liquid, consistent with solid ice but brighter than typical rafts. It appeared in 2 more passes in 2014, then disappeared. No breakup debris, no drift track, just gone. The pattern recognition algorithm flagged 3 more transient objects in Punga Mare and Kraken Mare between 2012 and 2016. All appeared for 2 to 5 flybys, all vanished without trace, and all shared the same anomalous brightness temperature, 92 K, warmer than liquid methane at 90.7 K, but colder than expected for exposed water ice at 94 K. One hypothesis proposed nitrogen ice. Titan's atmosphere is 98% nitrogen, and at high altitude it condenses into particles that drift down. If nitrogen snow landed on methane lakes, it might float briefly before sublimating or dissolving, creating temporary radar-bright patches. But nitrogen ice sublimates fast at 90 K, within hours, not the weeks between Cassini passes. The objects would need to be resupplied constantly, implying active venting beneath the lakes. That brought the focus back to cryovolcanism. The exotic ice hypothesis emerged from high-pressure lab work. Researchers at Cornell subjected water ice mixed with ammonia and methane to 20 kilobar pressures, simulating conditions 150 kilometers deep in Titan. At 176 K, the mixture crystallized into a structure with radar reflectivity 6 times higher than pure water ice. If tidal heating warmed Titan's deep interior to 176 K, this exotic ice could form and then erupt, rising buoyantly through the ammonia-water mantle until it breached the surface. Once exposed to Titan's 94 K crust, it would cool and revert to normal ice in 3 to 7 days, which aligns with the transient object timescales. The second object wasn't in a lake. It showed up in radar images of Tui Regio, a bright equatorial zone far from any liquid. The feature, 3 kilometers across, appeared in a 2015 pass and persisted through 2 patches in 2016, then vanished. Its radar cross-section suggested a rough surface, not smooth like a liquid spill. VIMS detected a weak 2.0 micron absorption at the same location, consistent with water ice mixed with organics. The brightness temperature was 95.1 K, warmer than ambient by 1.4 degrees. That thermal excess, sustained over 14 months, required an energy source, either radioactive decay or residual heat from a recent eruption. The timeline problem looms over Dragonfly. The mission launches no earlier than 2028, arrives in 2034, and operates for 2.7 Earth years, roughly 1 Titan year. Cassini took 13 years to catalogue the global changes scientists are still parsing. Dragonfly has 34 months to find what Cassini missed. Its landing site, Selk Crater, sits in Titan's equatorial dune fields, 1,700 kilometers from the nearest methane lake and 3,200 kilometers from the radar-silent zones. The mission trades close access to active geology for safer landing terrain. If the exotic ice eruptions are real, Dragonfly might never see one. But Selk has its own mystery. VIMS imaging shows a 5 kilometers dark streak extending northeast from the crater rim, too straight to be a natural channel. Its spectral signature matches liquid hydrocarbons, but the terrain slopes uphill, away from the crater. That inverts the expected flow direction. One model suggests a subsurface methane aquifer breached during the impact that formed Selk, fountaining liquid uphill through fractures. If Dragonfly drills into that streak, it might sample organics from deep in Titan's crust, chemistry untouched by atmospheric radiation for millions of years. The new map, released in 2021, synthesized 120 radar passes into a global mosaic at 1 kilometer's resolution. It revealed 674 impact craters, far fewer than expected for a 4.5 billion-year-old surface. Either Titan's crust is young, refreshed by cryovolcanic resurfacing, or craters erode fast under methane rain and wind-driven sand. The map also confirmed the labyrinth terrain covers 9% of Titan's high latitudes, a fractured landscape of ridges and valleys with no parallel in the solar system. The valleys run 400 to 600 meters deep, too narrow for rivers, but aligned with tectonic stress models. If tidal forces crack the crust periodically, the labyrinth might be an active fault zone. Cassini's final pass, the T-126 flyby on April 22, 2017, took it within 979 kilometers of Titan's surface. INMS measured atmospheric hydrogen at 1.1 ppb, up from the 2010 value of 0.7 ppb. That 57% increase over 7 years could reflect seasonal variation, or it could mean the metabolic sink weakened. The data embargo lasted 18 months. JPL released raw telemetry in October 2017, but the calibrated science products, corrected for instrument drift and noise, didn't arrive until March 2019. The delay sparked rumors of contested findings, but the real bottleneck was understaffing. Cassini's science team had shrunk from 250 to 60 after the mission ended. The official statement, issued by NASA on July 12, 2019, summarized Titan as a world in equilibrium. The methane cycle, the organic chemistry, the surface geology, all fit within known physics. No biological signatures confirmed, no unexplained energy sources, no artifacts. A strange world, but not inexplicable. The forbidden hypotheses live in the appendices of conference papers, models explored but not endorsed. The artifact hypothesis, that the radar silent zones conceal engineered voids, appears in a 2016 preprint by Jani Radabau at BYU. She calculated that a hollow structure 200 meters down could match the gravity and radar data, but offered no mechanism for how it formed. The Drake equation revision came from David Grinspoon. He argued Titan proves life's requirements are broader than we assumed. If metabolism works in liquid methane at 94 K, then the habitable zone extends to cold moons around gas giants in every stellar system. That multiplies the Drake equation's final term, the number of planets where life develops, by a factor of 10 or more. Dragonfly will tell us. Until then, we wait. If you want more deep-dive space documentaries walking through the questions we're still asking, subscribe. We'll be here when the answer comes back.